So we're going to start with Debes from Space Telescope, who's going to give us details about exoplanetary observation with a Roman coronagraph. So all yours.
Great. Hey, everybody. Does this sound okay? Awesome. I got a thumbs up from the back. Well, thanks to the organizers for inviting me. Before I get started, when I was a wee grad student, I gave a presentation at the Carnegie Institution of Washington. It was on direct imaging for planets around white dwarfs. And there was this older woman in the audience who kept asking very probing, very insightful questions the whole time throughout my talk. And at the end, I turned to someone and I said, "Who was that? I don't know who that was." He said, "Oh, that's Nancy Grace Roman." And so that was my first experience with her. She was a wonderful woman. And so it's very exciting to be talking today about a mission that's named after her. So I'm going to talk about the Coronagraphic Instrument on Roman, or CGI, and what its potential might be for surveying nearby planetary systems. It's a technology demonstration. It's a pathway to something like the Habitable Worlds Observatory, where we're going to do extremely high contrast imaging looking for Earths. But Roman in its own right has the potential to do a lot of really cool and wonderful science that can also help us get along. And one click. Get the pump primed. All right. See, I even practiced this ahead of time. Okay, so if we looked at our own solar system from 10 parsecs away, right? This is sort of something we might see if we were looking at it with the Habitable Worlds Observatory. I mean, this is very idealized, but if you had the ability to look at our own terrestrial planet area, right, the inner 10 or 12 AU, you'd see a sort of a fuzzy, bright dust. This is the zodiacal cloud in our solar system, and we expect other solar systems to have similar things. This is caused by some combination of dust created from asteroid collisions or comet disintegration. And then, of course, we have our planets. And then if you zoom out a little bit, right, you have the giant planet region, which is sort of encompassed by some more dust, probably from the Kuiper belt, right? And that dust interacts in some ways and creates like resonance structures with the giant planets, like with Neptune. And if you somehow had a perfect instrument, you could see all of this and really map out the solar system in a level of detail that we really don't have the capability of currently. But I would say that Roman definitely has the potential for doing something close to this for some of our nearby stellar neighbors. The problem, of course, is that for every photon of light from the sun that gets reflected off the Earth and hits some alien observer, 10 billion photons come off the sun. And that's a really huge challenge, to reject all that light from a star so that you could see something like the Earth from far away. And that's the whole point of this technology demonstration for CGI. And we're trying to answer these big questions about planetary systems. Like, what is a typical planetary system architecture? We have a lot of information from a lot of other different planet detection techniques, but they all have their biases. And so it's really hard to know what is a typical architecture. Is it sort of a chain of terrestrial and Neptune-like planets that's very close to the star? Is it more like a giant planet-dominant system where there are a lot of dynamical interactions between these big giant planets and maybe not a lot of terrestrial planets? Or is it something more like our own solar system? These all exist, but we don't really know the relative fractions of each. And so getting at sort of a typical planetary architecture is a really interesting question to answer. Additionally, all these planetary systems have some sort of remnant minor body population, asteroids and comets, and these interact with the planets or with themselves to create a lot of dust. And dust is very easy to see, especially in reflected light in the visible. And so that is either someone's trash, if you're a direct planet imager and you don't want a lot of dust in your system so you can characterize the planets, or it's your treasure, if you're someone like me who likes disks and wants to understand the composition of the minor bodies, which tells you something about the building blocks of planet formation. In any case, these kinds of questions impact what we understand eta Earth to be, that is the fraction of planetary systems that might have an Earth-like planet. as well as what is the visible light brightness distribution of exozodies. And that's important because we need to know what the background for our planet detections are, and that determines how long our exposure times for characterization or anything like that. So these are the two biggest, in my mind, astrophysical drivers to risk for a particular habitable worlds observatory Earth-like planet yield, right? People talk about yields of Earth-like planets, and we want to get a statistical sample with HWO. And these two uncertainties really drive our inability to predict accurately what that might be. In comes the coronagraphic instrument, which had been designed as a pathfinder for very, very high contrast imaging, for some sort of Earth-like planet detector. Well, now we have the Habitable Worlds Observer as like a main priority of NASA. And one of the things that we need to be able to do is demonstrate that we can get very extreme contrast ratios in space. And that's not easy to do. So this is the actual layout of CGI, and I could probably spend an entire 25 minutes talking about every little piece of this. But suffice it to say that this is one of the most optimized coronagraphs that will ever fly in space once it's launched. I've worked many years on the coronagraph on Hubble through the STIS instrument. That is literally the least optimized coronagraph in space. It barely has a LEO stop, which is really critical for high contrast imaging. And it has these hard wedges and bars that are the occulters. So it's a very simple system, and it does amazing things. So I'm really excited by the fact that CGI has low order wavefront sensing and control. This handles things like the focus changes of an instrument due to flexures in the optics. It handles the jitter of the spacecraft and makes that much lower. Those are all really important for gaining high contrast. And then the other thing is the high order wavefront sensing and control. We essentially have put an extreme adaptive optics system in space. And instead of correcting the atmosphere, we're correcting all the little time changing things that an observatory goes through in space, corrects those to give you the highest contrast possible. And of course, what do I mean by contrast? Okay, this is just the flux ratio of a planet or a disk relative to the star flux, right? And so, like I said, for every photon from Earth that gets reflected from the sunlight, there's 10 billion photons that are coming from the sun. And so that kind of contrast is 10 to the minus 10, right? So there we have Earth at 10 parsecs. Boy, that's really hard to do, right? And then you look at what we've been doing, and you understand why we haven't directly detected any Earth-like planets, because the contrast that we can achieve currently, you know, in our best cases is maybe 10 to the minus 7 at 1 arc second, right? Then we talk about what Roman's requirements are. This is detecting things at a contrast ratio of 10 to the minus 7. And you can see that there are some self-luminous planets that might be bright enough to be detected at sort of shorter visible wavelengths. And then what we hope happens, right, is that everything works really, really well, and that Roman CGI will get down to sort of a contrast level of a few times 10 to the minus 9 or 10 to the minus 9. And then there's sort of these two bands in particular, band 1, which is sort of V band, and that has the closest inner working angle. And then there's sort of a wider field of view imager that's band 4, essentially. So that's like a longer wavelength band, and these are all the wavelengths. So band 4 is sort of the 800 nanometers, and band 1 is the blue, then sort of V band, like I said. And then there's also a spectroscopy mode with CGI that allows for characterization, and that's sort of designed to overlap with our sort of closest inner working angle high contrast imaging. And in addition to the spectroscopy and imaging, there's also polarimetry that's possible with CGI. And then down here are some predictions for what reflected light planets, how bright they might be. And they sort of range maybe a few times 10 to the minus 9, maybe 10 to the minus 9. So that's pretty challenging, but these are the ones we know about. And of course, there may be others hiding that are a little bit more advantageous for follow-up with CGI. The really good news, if you didn't know, is that TVAC occurred for CGI, and they actually dug a dark hole in sort of space-like conditions for two of the masks, the hybrid Leo chronograph mask, or HLC, and then the wide field of view shaped pupil chronographic mask, or it has a long thing, but basically wide field of view. And they were trying to get high contrast at between 6 and 9 lambda over D. And that's sort of this ring here for the HLC and this ring here. And on average, they were getting a few times 10 to the minus 8 raw contrast. So raw contrast is not the same as detecting something at this contrast. This is what you start out with. You have all kinds of post-processing tricks and ways to improve your final contrast of what things you might detect. And so the fact that we're getting raw contrasts in a regime that is better than requirements, the sort of baseline requirements, means that this is very promising. And then I have a little movie that shows the dark hole that was being dug. These were slides that were presented at SPIE recently, and I'm just reprinting them. And this graph shows how the contrast sort of evolved over time as different iterations of control were being done. You can see that, you know, some of these bumps are when they tweaked things, right? But at the end, in this black line, they're getting well below their sort of requirements that they needed to get to, which is really exciting. And they could potentially have gone deeper if they had more time, but there was a limited amount of time to do this work. Okay, so what does that mean in terms of our potential? Well, science potential, right, is that you could look at reflected light from planets in the visible. So this is a region that we don't often probe exoplanets in. And so that's really exciting for things like metallicity, composition, the presence of hazes or not, clouds. These are all things that have been done to some degree with transit spectroscopy in the visible. But we can do this now with reflected light on much older and colder planets than what has previously been possible. And so that's really precursor planetary science for HWO. We might actually have some better predictions for what giant planets might look like for things like an HWO like larger survey. And of course, there are hotter exoplanets that are so bright in the infrared, they still emit a little bit of light in the visible. And so because we would sort of achieve a very high contrast with the CGI, some of our favorite exoplanets that have been detected that are sort of a few hundred to 1,000 or so Kelvin emit just enough light in the visible that they're at sort of, you know, CGI-like contrasts. And so you can do the same kinds of composition and haze and cloud studies that you might want to do with the colder planets that you can also do with the hotter, younger planets too. I mentioned debris disks, right? So, and especially our uncertainty about exozodies. We've only detected a few exozodi-like disks, and primarily in the mid-infrared. We have no idea how these things emit in the visible. We can make some guesses based on our own solar system, but we don't really know if our solar system is a typical dusty system. And so probing the habitable zone of nearby stars is really important for understanding, is this a dusty star or is this not? And these are very hard to detect, so we don't really know for a large fraction of nearby stars. So this, no, I'm gonna accidentally advance things. So if you look at the HabEx target list, which is very similar to what HWO will look at, the HLC field of view is very comparable to at least the outer edge of a lot of nearby stars' habitable zone. So you can probe at least the outer edge and see, is there any dust there? And then for maybe a dozen or so, there are also stars where you're actually probing the same insolation distance as the Earth around our own sun. So that's sort of like, for different spectral types, this moves around, but you can actually catch sort of the very habitable zone or Earth-like zone of a few nearby stars. So if we are able to get to very high contrasts, we can actually prospect for the presence of dust or absence of dust in a sample of stars. And again, just like for point sources and planets, you know, this high contrast is going to have a huge effect on our ability to study nearby dust disks. So I have a few famous disks like TW Hydra, which is a protoplanetary disk, and a few very famous debris disks that range in sort of contrast. And then you compare that to what we think HLC and SPC will do, And we're sort of in the range of tens of zodies in sensitivity around nearby stars. I mentioned polarimetry. So if you're a dust person, you love polarimetry because it gives you an extra constraint on the properties of dust. Whether you're in a galaxy, around a planetary nebula, or around a star, it all gives you sort of similar information about grain shape, grain size distribution, and these are the ways that you really learn something about the composition and properties of the dust that you're studying. And so too for debris disks. To give you an idea, in the visible, I think only 3 or 4 disks have been looked at in polarized light in any sort of way where you can get a polarization fraction as a function of scattering angle. So this is a whole like unexplored territory for planetary systems. And if CGI works as we expect, this is possible where we can get a lot of different constraints on dust composition and structure. And that's really, really exciting for planetary people because like I said, this is essentially the building blocks of planetary systems that we can study. So I can't believe that launch year is in a couple of years. That kind of blew my mind. I somehow lost 4 years, somehow, I don't know. But this is really cool. That's not a lot of time. That's like 700 and some days. I'm kind of freaking out about this. But it does mean that some things will have changed by the time that this is launched. And that's important for our thinking about like what kind of science CGI could do if it has the time and capability to do so. So for example, JWST, is right now following up a lot of really interesting giant planets that are sort of at a few AU that cause an RV signal that's sort of a trend. And then it's also causing an astrometric signal in Gaia compared to Hipparcos. So there's a whole bunch of like 5 or 10 planets that are really interesting. And if they get detected, they're kind of in that range of interest for CGI. So they may become CGI targets if they're discovered and characterized a little bit better. And of course, Gaia will release its 4th data release pretty soon, and certainly before launch. And that's when they'll start publishing astrometric orbits of nearby planets around stars. So perhaps within 20 parsecs or so, there'll be some interesting giant planets that we want to follow up in reflected light. Additionally, JWST has this fantastic mid-infrared spectrograph, right? MIRI, MRS, and LRS. That's very sensitive. So you can find like a few % excesses around nearby stars. So that's not ZODI level, but it's not debris disk level either. It's somewhere in between, sort of low luminosity dust disks. Think sort of like a dust disk around Epsilon Eridani. And presumably, we'll start finding some more. In particular, if you see a lot of, not a lot of like small dust, it creates a pretty strong 10 micron silicate emission feature, which potentially could be found around nearby stars. And there are many, many programs, from like a program I'm involved in looking at some gold planet candidates around white dwarfs, all the way down to Saturn type planets around young stars. But JWST in the mid-infrared and near-infrared will really start to characterize cold planets for the first time. And this will drive new models that hopefully will be around by the time we're thinking about what we're going to be doing with CGI. And that theory part of things is also going to, I think, be moving along in the next 2 years, especially on things like exozodies, where we have very little information, but we realize we need to start making some better predictions than what currently exist, as well as updates to planetary atmospheres via all these different new ways of characterizing planets. Okay, so that leads us to sort of 3 possible scenarios that we might have with CGI. And that first scenario is just sort of like the very baseline. We just meet the requirements of CGI, right? That's sort of like, that's definitely going to happen. It's going to be the sort of baseline first thing. And in that time, there's 90 days to do stuff, right? To test things out, to demonstrate all the requirements that have been laid out, and so on. That's 2,200 hours. That's not nothing. To give you some perspective, throughout Hubble's lifetime, high contrast imaging on STIS has represented 5 to 10% of STIS's allocation of orbits, which is maybe at best a quarter of all the orbits that get put onto Hubble. So we've done a lot with a little high contrast imaging with STIS. And so I can imagine, even if we have a little of this mission, we can do a lot of really exciting and interesting things. So what would that look like? Okay, well, we'd have some bright stars that get down to about 10 to the minus 7 contrast in our inner working angle. And so we could rule a few things out for these nearby stars, like very bright zodies, and maybe we could see some self-luminous planets. But the thing to keep in mind is we're still 100 to 10,000 times better raw contrast than Hubble coronagraphy with a dark hole, and 10 to 500 times better raw contrast than Hubble coronagraphy without a dark hole. So even if you're not doing the highest contrast possible, you're still doing way better than what Hubble can do now. And so even though you've done all the technology that you wanted to do, so that's a A+, you could do a lot of interesting things in the remaining 22-hour, remainder of whatever is left over once you've done the requirements. This is something that the CPP is discussing now, so this is not new, but I want the broader audience to think about this because anything you can currently do with HST would be possible and better with CGI with a better working angle, and you would have color, and that's not something that Hubble can do. So there's a lot of possible science in 90 days because at least in this situation, your time scale for getting to 10 to the minus 7 is pretty short, maybe like 10 hours. That's the requirement. So if you just sort of divide up 2,200 hours by like 10 hours per target and maybe 24 hours per dark hole, you get a few dozen stars that you could potentially look at. So that's not nothing and really exciting. I think that's going to be the very conservative estimate because as I said, we're already sort of getting 10 to the minus 7 contrast with Hubble on like a few stars that are like really, really, good for this kind of thing. And of course, TVAC's raw contrast is already doing better than what Hubble, when it's really trying, can do in an hour. Just to put things in perspective. So now let's think about it like we make our best estimated performance over our 90 days. And that opens up a lot of really interesting things. We sort of could do anything we could have done in the first scenario. Plus, now our sample of bright stars will have very high contrast imaging, maybe a few times 10 to the minus 9. And that opens up the ability to directly probe exozodies at sort of a few tens of exozodi levels of brightness. You definitely would catch a lot of self-luminous planets, or they would be possible. And then, of course, some RV planets would also be accessible. And, in this kind of scenario of order, you'd have a handful of each of those types. And again, polarimetry is now possible, not just on bright debris disks or bright type things. You could also do it on bright exozodies. And perhaps you could at least do the experiment to see if self-luminous planets or brown dwarfs have any kind of polarization. And I should point out, if a planet has dust around it, it'll actually have a polarization signature as well, which would be extremely interesting. You also could start pushing the limits of what CGI could do. Like, how well could we do when we're not performing at sort of very bright stars? And so you could go fainter on, you could explore going fainter with lower contrast, and that allows things like protoplanetary disks or debris disks out to much larger distances. So I would say in this scenario, you're doing transformative science, but maybe small numbers of transformative things, but still very exciting. Now, of course, if we have infinite time with good performance, many, many things are possible and exciting. Now, we won't get infinite time, but as an idea of some things we could do so that hopefully the community can start prioritizing these things and telling the CPP what they would like to do, I throw some ideas out. So, I said a large survey of HWO targets for zodies is really, really interesting because that retires some risk for HWO. And that you could get 70 targets in about 100 to 400 hours where you have a pretty good idea of what the zodi level might be for that star. You could follow up as many advantageous Gaia exoplanets in reflected light. You could follow up a whole bunch of new disks that will likely have been discovered at this point. You could explore different wavefront correction algorithm and approaches. That would also help HWO by like really getting things figured out for high contrast imaging in space. And then, of course, there's things beyond planets that we could do. I say accreting protoplanets, you could do circumstellar environments of massive stars, right? If you have no limit to how faint you can go, you can start doing interesting science with massive stars and their environs. You can look at bright QSOs and look at their environments down to a very small inner working angles. And then, of course, I want you all to think, if you had high contrast and a small inner working angle, what would you do? And tell us. And then just to point out, you can do high contrast imaging without a dark hole even. So Jessica Gerst-Range did some very nice simulations of sort of an observing scenario very similar to what the OS11 public simulations do, but we basically turned off the dark hole and just let the spacecraft vary as it varied. And with simple sort of reference differential imaging and ADI, we're getting to contrasts that are basically only limited by that variation. And that variation is of order in terms of raw contrast of a few 10 to the -8. So this would be as if things are working super, super well. We might even get very, very high contrasts even without building a dark hole. So I just wanted to put that out there as a possibility if things get extended. And of course, there are all these masks that have not been fully tested or commissioned that could now be done. And all of this really benefits HWO in the end. And you can ask me about exozodies some more in the questions if you want. So just to wrap up, CGI is on track to perform very well. It's really exciting. I can't wait. And if we are really in this regime where we're getting the best estimated performance, even in 90 days, there will be transformative science that could be done. And additional mission time is always welcome. So right now, the CPP is coming up with a community interest survey. So I encourage you to keep an eye out for that and reply and put your own science cases out there and start thinking about that now, because we are only 2 years away and maybe a few more years away from a review on whether there's more time to be used for CGI. So the time to think about things is now. So thank you.
Thank you, John. Question for John. Yeah, take a
Thank you for nice talk. Is there any criteria to the CGI can be open for the open use after
like
the
a
validations? General open use.
Yeah, so I think as I understand it, and we have people who are, know better than me in the audience who can correct me if I say anything terribly wrong. But the idea right now is you have 90 days to do a technology demonstration, right? That's the nominal mission at this point. And so once that's done, as Julie said, there's going to be a review to see what could be possible beyond that. So if things are working very well, the community should definitely advocate, if they think there's a good reason for it, to have sort of an opportunity to do more generalized science. But right now, the mission is to get the technology development done, and the CPP right now is determining how to distribute the existing time to meet requirements and then demonstrate whatever they need to demonstrate about the instrument. And hopefully that wasn't too bad.
No, it was great, perfect. I wanted to, we have for a long time referred to that 90 days as a tech demo, and I think that sometimes conveys an incorrect impression, because the actual amount of time needed to demonstrate, the basic minimum requirement is actually quite small. So the vast majority of that 90 days is for whatever else people should do. So I would strongly encourage everyone to not wait till some mythical time in the future to say what you think should happen with the coronagraph instrument, but engage right now. Particularly if there are, potential concerns about lifetime, you would be absolutely bananas to keep your ideas to yourself, waiting for extended operations. Like Whitefield, there is going to be more really compelling things that we want to do, then will fit in the mission time. But we want all the ideas out now.
Yeah, I agree with that completely.
Hi, John. You phrase this mostly in terms of sort of one shot, can you detect it or not? But I know a lot of the discussion with HWO is about the appropriate cadence to detect objects and characterize orbits and things like that. Do you have any plans to study, reproducibility on longer timescales and things like that?
Oh, that's interesting. I have not thought about that, but there are plenty of people on the CPP. So what I would say is, I talk to as many people as you can and see if they're thinking about it and raise that as an issue. Certainly coordinating with what the HWO like START and TAG teams are thinking about is really good. And I'm sure the CPP is on it. I should be, full disclosure, I'm just a collaborator. I miss half the meetings, so I'm not the only person to talk to about this. Yeah, Vanessa Bailey, for example, is in the audience. She's a great resource for the latest and greatest on CGI as well. Yeah, but like I said, I'm also happy here before everyone leaves to, if you have an idea and you want to even see if it's possible, I'm happy to sort of workshop and brainstorm with people, or after the meeting too, or point you to people who are more expert in that.
All right. In the interest of time, we're gonna move to the next talk. So thanks, John, again.
Yep, I'll be responsive on Slack.